All right, now, here, good morning again. We're going to be writing down answers for the final exam in 477. All right, now for problem 1 is true, false, we have false. For B and C, we have both true. Quicksort is n squared in the worst case, but n log n in the average case, or so forth. So we can usually say it's omega of n log n. All right, now the next one, no negative weights is a requirement for Dijkstra's algorithm. In dynamic programming, you have to work the subproblems in topological order, because each one has to be worked before any that are dependent on it. In problem C, if there are paths, undirected path between any 2 points, those 2 points are in the same component. Likewise, if you have 2 points in a directed graph, they're in the same component if there is a directed path between them in both directions. Now, here we have E. If the number of edges equals n, the number of vertices log n, then the graph is sparse. The master theorem. And it's based on the fact that 2 squared is 4, or the base 2 logarithm of 4 is 2, same thing. And it's omega because that's greater than or equal to, so it's n squared log n. On this one is simple antiderivative. F of n minus f of n minus 1 is n over 4. So it should be n cubed over, no, n squared over 8, which of course is theta of n squared. This is 3D. This first problem here with the square root, we move this other term to the left and then divide by the square root of n. It looks like I shouldn't have written this. This is not f. This is square root of n itself. There we go. Okay, now that equals 1. And so we can write f prime of n as 1. So f of n is theta of n. Moving along to number 2e, I know there's a complicated substitution way to do this. However, I would have expected you to remember that the answer is theta of log star n. All right, now moving to this one here. This is antiderivative. We subtract g of n minus 1 from both sides and divide both sides by 2. And the answer is theta of n cubed. All right, the next one is simple antiderivative. The antiderivative of n is n squared. It's omega because that's greater than or equal to. H is more complicated. You have to do a substitution. So if h of n is less than or equal to 2h of the square root of n plus all of log n. Well, we know because of this less than or equal to and the big O that we know that the answer will be big O. But other than that, we're going to do the substitution n equals log n, and we let h of n be g. So we introduce a new function g of n, but since m is log n, that's g of log base 2 of n. Now, what's h of the square root of n? Well, substituting here, it's the base 2 log, or g of the base 2 logarithm of square root of n, which is g of half of the base 2 logarithm of n, which is g of n over 2. Now we substitute back into the original inequality, and we get g of n, this is g of n, and this is 2 times g of n over 2 plus, now log n is n, so we have O of n. Now, using the master theorem, that becomes g of m is O of m log m. All right, now we substitute it back in. This is f of n, and log n, m is log n, so n of O of log n times the log n. All right, now we'll go over to problem I. F of n is f of n over 2 plus 1. Now, you already know that the answer is log n, but let's go through some steps here that we can show it a different way using substitution. let m equal the base 2 logarithm of n, which means that n equals 2 to the m. Now, that means that we're going to let g be the function, so that g of m is f of n, which means g of m is f of 2 to the m. All right, now, here is where it gets interesting. This long equation here. We have f of n over 2, so that's f of 2 to the m divided by 2, which is f of 2 to the power of n minus 1, which by this equation is g of m minus 1. Substituting back in here, we get g of m equals g of m minus 1 plus 1, which means that f of n, which equals g of m, is theta of m by the master theorem. Actually, no, by antiderivative, which is theta of log n, which is what we knew from the beginning. All right, now for part J, we simply use antiderivative. So the antiderivative of log n is n log n. Well, it's theta of n log n, but we have an O there, so we put an O here. So the answer is O of n log n. Simple antiderivative. All right, now for K, f of n is f of n over 2 plus 2 times f of n over 4. All right, now we don't have the same number there, so we use the generalized master theorem. And of course, n is simply n to the power of 1, so that's the value of c. So we take 1/2 to the power of c, which is 1. 2 times the 4th to the power of 1, which is that, so it gives you 1/2 plus 2/4, 1/2, and that's equal to 1. So that means that the answer has the log in it. Well, it's going to be theta of n log m by the generalized master theorem. All right, now we'll go over to problem L. Here, we have 3/5 and 4/5. This is once again generalized master theorem. And we have c equals 2 here. So we take these two coefficients and square both of them. You get, of course, 9 plus 16 is 25. You get 1. So therefore, the logarithm is in the answer, so it's theta of n squared log n. All right, now, there's more room on the whiteboard, so I'll start with the first part of problem 4a. For int I equals 0 to n I plus plus. This problem is just a warmer. I mean, it's really trivial. The answer, of course, is theta of n.
1.
All right, now b, we're going to double the index after each iteration. So we let j equal log I, which means I is 2 to the j, and 2i is 2 to the j plus 1. Another way to look at it is the base 2 logarithm of 2i is 1 plus the base 2 logarithm of I, which is simply j plus 1. And we let m equal log n. And we now change the initial loop to j goes from 0 up to m, incrementing by 1 each time. Well, from problem A, we know the answer is theta of n, which means it's theta of log n. All right, now, problem C is the next step up. We're going to square the index at every step. So, once again, we let j equal the base 2 logarithm of I. Now, the base 2 logarithm of I times I is 2 times the base 2 logarithm of I, which is 2j. And we're going to let, again, m equal log n. So we rewrite the first line as j goes from 1 to m, and doubling j every time. But we then apply the result from problem B, and we get that the answer is theta of log m. But then m is log n. So the answer is, whoops, it's theta of log n. That's the answer.